today, but we might be able to talk about that. Anyway, so going with this, this is the shortcut I'm going to give you in terms of memorizing the exact values of 30, 45, and 60. So recall, I assume you know how to construct the triangles for them. Yeah. So you can always do that as a safety. But here, cosine is going from 1 to 0. I'm going to tell you right now, there's only 3 kind of values for cosine and sine for these exact solutions. Yep, 1/2, root 2 over 2, and root 3 over 2, exactly. And in increasing order like that, right? Exactly. So one of them is going to go decreasing order because 1 to 0 will be decreasing. So we go root 3 over 2, root 2 over 2, and then 1 over 2. And then for the other one, it goes from 0 to 1. So I'm going to go 1/2, root 2 over 2, root 3 over 2. And what happens if I want to know the sine tangent values? It'll be y over x, because we've also discussed one of the identities. So another thing you're going to have to do later on is this thing called identity, which is kind of like a puzzle. I think we can preview that today. So one of the truth, or I guess established equations, is that tan theta is equals to sine theta over cos, which in this case, yes, it corresponds to the y coordinate divided by the x coordinate. Okay, so that brings me to the first task I need you to know how to do. We're going to go sine theta. So I'm saying some kind of angle is going to give you root 3 over 2. Actually, no, that was the second task, I think. We didn't get to that. Oh, okay. Yeah, so I need to specify, first of all, what angles in terms of domains that you would need to know. Okay, so you're saying right away you know it's 30 because, you know, you can either look at the chart. Actually, no, it's not 30. It is 60. No. So we're saying what angle, so sine of what angle will give you, oh wait, no, it is, wait, it's 60. Wait, you said 30. Yeah, it's 60. Yeah, it's 60. Because the sine of the root 3 over 2 will give you 60. Yeah. So this is how you're supposed to do them, though. If this was a calculator question, so 2 flavored. This is a non-calculator version. Non-calculator. And then you're going to see the version with calculator. Okay, we're going to work on them just pretty much the same thing. So this would be a calculator question. Calculator is if they give you, let's say if they actually give you root 3 over 2. So let's say if they give you 0.866. Okay? Well, 0.866 is pretty much approximate value for root 3 over 2 anyways. But if they give it to you in a decimal like that, you're probably not expecting you to do it exact solution. For this one, you're going to just sine -1 both sides. Okay, so sine -1 both sides. If you sine -1 of that, you get sine -1 of the answer. Yeah, you should get 60. Okay. And then for this no calculator version, you should just recognize root 3 over 2. Right? You should just know root 3 over 2. Either way, theta equals 60, but you're not done yet. Okay? Recall that I gave you the shortcut for cast. If you don't remember the unit circle, if there's one thing you should remember is that cast, and also you should remember the names of them, meaning theta, 180 minus theta, 180 plus theta, and 360 minus theta. Yeah, you should know that. All right, so how do I use this cast in this case? Well, I'm saying that 60 is this angle right here. So I know 3 other places that have the exact same magnitude, root 3 over 2. But only one other place have positive root 3 over 2. And that's going to be in the quadrant of S as well. So S, again, this is 60. So I know this one's going to be, this one in the it's going to be -3 over 2. I don't really care for it, right? I'm only caring for the positive. So to get the other one, theta 2 would therefore equals to 180 degree minus 60. because it's almost like I go a whole 180 degrees and then I backtrack 60. So that's going to be 120 degrees. There we go. Been sleeping late as well. Yeah. Theta, so 60 and 120, and you're going to be doing the same thing for the other one. Now, what happens if sometimes you are left with a, let's say, negative number, so negative 1/2, okay? I suggest you, there's two ways of dealing with this. I suggest you do it like this. I suggest when you do the sine negative 1, you actually don't solve for theta, but you solve for the beta. So I'm just going to give you a different letter. So I'm calling this the beta right here. So these small angles, I'll call that beta. So in this quadrant, beta is equals to theta. In this quadrant, I'm going to revise that. The theta, which is the big angle, is 180 minus beta. So 180 plus beta. Yeah, all I'm saying is I'm changing this now. I've used to call the big angle and the small angle theta. So I just want a way to separate them. So the big angle, meaning this is the one, so the, theta is 120, then that little angle there, beta, is going to be 60. Okay, so what I'm saying is you should find out what that small angle is by finding the absolute value version. So you take the absolute value. So that ensures that you always solve for the first quadrant. Okay? Because if you don't, let's try. Put in sine negative 1 of negative 0.5. You will get an angle that's not, so negative 30. So then there's two things you got to deal with. Negative 30, you got to first of all add 360 to get back into your angle. So you're like, 330. I know that means I'm in my fourth quadrant. Then if you do it this method, then you have to figure out what the small beta is. You're like, okay, if this is 330, the little beta must be 30. Okay? Then you got to go, I want the other negative quadrant, so I want tangent. So tangent was 180 plus beta. I figured out the beta earlier was 30. So then it'll be 210. Sorry, this is 30 as well, so then it'll be 210. But that's not the method I'm going to go with right now. Mine is going to ensure that I always get to the first quadrant first. And the way I do that is I always do sine negative 1 of the positive version. So if I do the positive version, I know right away my beta, so positive version, 1/2, I know my beta is going to be 30. So right away I know 30. Then I can just go pick the one I want. If it's positive, I pick quadrant 1 and 2. If it's negative, I pick quadrant 3 and 4. So therefore, I'm going to say theta is going to be equals to 180 minus 30. And then theta is going to be equals to 30 as well. So 30. So therefore, I have theta equals to... Wait, it's not 30, is it? It was 6. Wait, is it 30? Yes, it is. Sorry. It's 30. And it's also 150. Okay, we got that. All right, so now you can do one of those. So we're gonna go with, let's do a little bit tricky this time. Let's do tan. Tan theta is equals to negative root 3. Yeah, so your first move, sorry, I kept moving around. And I need to specify, I'll teach you how to do the full solution, if anything. And actually I'm going to make it a little bit different as well. I'll make it 0 to 720. Yeah, so first thing first is like this. So last time we worked on a different kind of problem. Last time was I told you what, let's say tan 30, and I needed you to find out this. Okay? So calculator version first. If you want to do calculator version, we're just going to go tan 30, right? And that's going to be equals to 0.577. This way, I'm trying to get rid of tan first. So the first move calculator way wise, I'm going to tan -1 both sides. Yeah, but remember, I do a absolute value on that though. So therefore, I'm actually going to say instead beta is equals to that. So beta is going to be equals to that. So beta is going to be equals to tan -1 of √3. But because whenever you see these √3, √2, you should think about exact solution. So then if you're doing the shortcut, I would quickly do something like this. I would quickly just draw 3 lines like that and just remind yourself that, you know, the first number needs to be going down, second number is going up, right? You can be like √3 over 2. Takes 2 seconds to write that, right? And then this one, oh, sorry, wrong way. So this one, oh, it is the right way. Sorry, too early. 1 over 2, and then the other one goes bigger and bigger, so 1 over 2, √2 over 2, and √3 over 2. Now, tan is the y. Okay, good, 60. Yeah, so you know beta is going to be 60, but beta is not the one I'm looking for. So what are my theta going to be? It'll be 180 plus. So let's see. How do I label this? Cast, right? So which 2 quadrants am I looking for? I'm not looking for this because it's tan. I'm looking for these 2 because those 2 are where tan is negative. Remember, cast shows the quadrants for which each of the trigonometric ratios are positive, right? So. Oh, sorry. No. That was confusing. I meant to say these 2, S and C. Yeah. Because this one is positive. This one's only sine positive. That means tan's negative. This one's only cosine's positive, so tan's negative. Yeah. So let's do that again. So theta is going to be equals to what? Oh, because look at this. I'm looking for negative, right? When does tan have negative ratios? Tan have negative ratios not at the all, but at the sine and the cosine quadrant. Because this t. Yeah, both of them. Oh, you were asking which one? Yeah, most of the time you're going to have 2 solutions for these kind of problems. From 0 to 360. Exactly. Yep. So we're gonna end up with 120 degrees and 300 degrees. But let's pay. Yeah. But almost. One more thing to consider. This is the domain for me. I said between 0 and 720 instead of 360 this time. So what you need to do is go 1 whole circle for each of them. Yeah. So theta is also going to be 120 plus 360, because you know the one at 120, if you add a 360 you end up back at the same spot. So 480 is another viable solution. And then finally you have the 300. That's not a negative 300, careful. 300 plus 360 is going to be equals to 760. Alright, let's do another one. This time cosine, I guess. Cos theta is going to be equals to, let's go negative √3 over 2. Yeah, the x coordinate. Yes, exactly. You're looking for those 2. Yep, that is right. So this time I did not specify a domain on purpose because I wanted you to show you yet another flavor. If your teacher asks you to find all solutions, okay, this is how you're gonna express it. Because technically you're gonna add 150 by 360 forever, basically. So there's actually infinite many solutions. To represent that, we're gonna go theta is 150 plus k times 360, or I guess 360k might be better. 360k. So 360k, and then I'm gonna write comma where k is element of all. What's a good number? Are negative number natural numbers? Oh damn it. Let me check natural number because I want a way to represent 0, negative. Oh, integer, right? Integer good. Maybe I. Right, because integer includes positive and negative whole numbers and 0 as well, right? Yeah, so that's what I want to do because 0 would indicate 150, while all the negatives means going backwards 360, and all the positive numbers will be forward 360. Yeah, so this is how, if they don't specify, yeah, this is how you're going to write exactly. There you go. Yeah, so this is how, yeah, when your internet lags a bit, it's harder to write. Yeah, okay, so that instead will be my full solution for this one. All right, so let's go back to the first kind of problem now. So I kind of worked them in different order. I meant to do this one first. So the first kinds was like this, sine, and I'll make it a little bit harder right now. So how about sine 900? So sine 900 equals to what? Basically, I guess equals to y. Solve for y. So solve for y. And now you can begin seeing them as like this, as a function. Y equals to sine x, or y equals to cos x, y equals tan x. Last time was basically given the y, I find the input. You know, that's always more annoying, right? Even for quadratic, when you're given the y and you need to solve for the x, you know, you got to use like quadratic equations and all that. But it was a much easier solve. It's always a much easier solve when you're given x instead and solve for y. And that's what we're doing right now for this kind of problem. So, you know, these are basically just inverse of each other. Okay, so do this. This is actually very easy if you're allowed to use calculator, right? Because you're just going to punch that into the calculator. Sine 900. And sine 900 gives me, 0. So sine 900 gives me 0. So let's see why it gives me 0. So the way you're going to do it by hand, if you have to do exact solution, is first of all, let's subtract or add 360 till you get back into your circle first, your primary circle, which is from 0 to 360. So I'm basically going to say that sine 900, well, that's the same thing as saying 900 minus 360 minus 360, yeah, 180. So that's the same thing as saying sine 180. Then you can go like, well, 180 is one of the special ones I'm supposed to know. That's on here, specifically the y coordinate for this one. So this is a -1 and 0, so I know this must be equal to 0. Okay, so sometime it might involve something like this though. So what happens if it's, let's say, instead 410? So 410, nope, not a good number. 405, yeah, 405 is better. So 405 again equals to what? We need to solve for this. Yep, so it equals to sine 45. And then what is sine 45 basically? Root 2 over 2. So you got it. Root 2 over 2. Okay, now I'm going to give you a slightly different flavor. So sometimes they might ask you in terms of a negative. So how do you deal with that? Okay, let's use something else this time. Let's do tan or something. Let's do tan negative 240. Exactly, yeah. So you're just going to add 360. So that basically turns into 240 plus 360. Yeah, 120. And then tan 120. It's going to be negative 1.732. Okay? Now, I'm going to give you the third type of problem, and then these three problems are going to give me the bread and butter, so the most basic problems for these chapters. Let me just find that really quickly. Tutor, grade 11. Okay, you know what? I'm just gonna give you one problem to solve as I look for it. Okay, actually, I'm gonna get you to think about this one. This is gonna be a slight tricky. So this is gonna be one level up from this kind of problem, the first kind of problem. 2 theta equals to, and let's stick with sine maybe. Sine. Let's do, it's root 3 over 2. So sine 2 theta equals to root 3 over 2. And then solve for me for between 0 and 360. Okay, wait. Alright, 0 to 360, go ahead. Yeah, you can. I'll let you do a little trick. I'll show you the little hint. So you're gonna first move is to let u be 2 theta. So this reverts into sine u, and then you can look for u first and then sub it back in after. Yeah. Yeah, nothing's negative. Yeah. Yeah, so I know I've do a lot of the negative ones at you already. Yeah. You still have to do U1, U2. Yep. Good. Now, here's one thing you need to consider when this happens, though. Okay? And I don't expect you to know these, so I didn't want to actually even throw this question at you until after we've learned graphing. Okay, but have you ever graphed a sine graph? No. Okay. Yeah, I'm going to I'm going to quickly introduce that concept a little bit. I'm definitely going to go into a lot more detail. But right now, just know that sine graph, if I were to plot it, this is how you would plot it. I'm going to split that chunk into 360s. So it's basically going to go by 90, 180, 270, and 360. Okay, the way you got to know the points for the sine graph, and this is for a sine graph. This is y equals to sine theta. So this is like the most basic function. So you know how when we learn function, we learn the family function, the basic most root function. So for quadratic, it'd be y equals to x squared. For linear, it'd be y equals to x and all that. Okay, the way I know the coordinates for these will be from that chart. I kind of built that earlier. So that was the thing with the y coordinate at these axis points. So that's talking about, so this is 1 and 0. Yeah, exactly. Yeah, 0, 1, negative 1, 0, 0, negative 1. Okay, so can you tell me, at 90, what is sine theta going to be? What's sine 90 going to be equal to? What, sine, second coordinate. So the y coordinate. 0, okay. So oh, did I ask you 90? Yeah, I asked you 90. My bad. I am too early. All right. So yeah. So sorry. At 0 would be 0, and I asked you 90. My head was thinking 0. So yeah. So 90 is at 1, and then at 180. Yeah, and 270. Yeah, and then 360. What happened? It looks funny. Oh. Oh, okay. Good. Okay, so that's that. That's the shape of the sine graph. Okay, so it's gonna keep repeating. So now actually I'm gonna explain to you what we basically did earlier in the two problems. So the first kind of problem that we did was basically saying, hey, I got a number here. Let's say root 3 over 2. We've been using root 3 over 2. Root 3 over 2 is basically 0.866. So we're basically saying between 0 and 360, what are the numbers that intersects at the 0.866? And we found that there's two solutions there. What you basically find is the first quadrant. So the first quadrant corresponds to this part right here. Okay? So so let's say you found it. You said it was root 3 over 2 for sine, it'd be 60 degrees. So we're basically saying it's 60 degrees. So probably a little bit higher than that. Oops. So probably up here. So it's because it's closer to the right a little bit. Okay. And then what did you say? So you first of all you found it was 60, and then you did your cast and you said, oh, it was also 180 minus 60. Let's look at what 180 minus 60 means. 180 minus 60 means I'm going all the way here and I'm subtracting 60. So what I'm saying here is, if this is 60 from here to here, it's got to be 60 from here to here also. You see that? Yeah. And then, so that's why, see, now it's going to be different if you do, let's say, something like cosine. Okay? So if I do cosine, when is cosine positive? Well, actually, I don't have cosine on here. So actually can't do that. But when is it negative? If I do negative, then I go, well, if I find beta first, this is 60 going to there. Then I go 180 plus 60 is going to give me down to here. And then the 360 minus 60 is going to get me down here. So you see, this corresponds to the bottom two quadrants, the C and the T quadrant, the number 3 and 4. Anyways, okay. But this is not actually what I wanted to show you. I wanted to show you this because what happens when I put a 2 there? So I know we haven't learned any transformations yet, but what does it mean, you think, when I put the... Okay, I like that you went with bigger and smaller instead of the shifts. So at least you know that this is multiplying. So you know it's one of these guys. So do you recall this equation at all? Y equals to A f of k x minus d. Yeah. So we're going to fit that onto here. So let's see how we can fit that onto the sine and cosine and tan graph. It would be k, exactly. Right. So it's A sine of k x minus d, because f of x, this is basically the x. I'm replacing x with k times x minus d. That's the rule of thumb. If you know how to write the parent function, just replace x with k bracket x minus d, and then put the a times everything. A can be multiplying the whole thing. And then the whole thing add or subtract c. So yes, you're right. So then that k, and you know k is opposite, right? K is opposite of what you think. So yeah, so instead of saying bigger, Smaller is what I wanted to hear, and horizontally. So horizontally compressed by a factor of 2 is what I wanted to hear. So what that means is going to look like this now. So I'm going to break this off into finer chunks. So you're actually going to see this right here. And that means I can actually fit two of them. I can actually fit two of them into one cycle. So you see that? So that means I got squished horizontally by 2, right? Because I now fit two of them. I'll tell you how to deal with these graphing all in one session together. I'm not sure if we'll get to that today. But I want you to I want to show you at the 0.866, how many solutions do I have now between 0 and 360? So 0.866. Remember, that's up here. So how many times does that intersect with my function now between 0 and 360? 4. So when you tell me it's it's, oh, by the way, why did you multiply these by 2? Oh, no, you divided by 2. Never mind. You went this way. You divided by 2. So yeah, so you found there's 30. So I found it's 30 here and it's 60 here. Right, it'll show up again later because this time we got compressed. This is how you find it. When you compress it by a factor of 2, okay, it means your period is now 180. Period is how far you go in the x direction before you repeat again. Yeah. You did that for your physics unit. Okay. So what we're going to add, back then, when we needed more solution, we added 360. This time the period is now 180. So what you do is you add 180 to your answers. Okay, so you add 180. Yeah, so the next data is going to be 30 plus 180, which is 210. And then, yeah, you said the other one is 60 plus 180, and that's going to be 240. So 1, 2, 3, 4 solutions right there. Okay, so don't worry too much about this. We'll revisit this after we start graphing again. But right now, I gave you a quick intro of how to graph. And at the very least, I need you to know how to graph the parent functions now. And that's, you can start from the unit circle, right? Everything comes from the unit circle. All right, so now this next problem is that third bread and butter problem I was talking about. And this is how it goes. So this time, instead of a unit circle, they actually give you a multi-unit circle. Multi-unit circle meaning the radius of that unit circle is actually not 1. Okay, so they're saying the point 20 and 21 is on a terminal arm of an angle theta in standard position. So what they're saying is this. So we can build that. So right now, so unit circle 20 and 21 is in the first quadrant because positive for both coordinates. So I can kind of draw that in. So I'll draw in a unit circle. I don't really need to draw the circle, but just to show you this relates to the unit circle. So I'm going to go 20 and 21 is pretty close. So I would just say probably look something like this, right? So that would be point 20 and 21. Meaning if I construct this circle, this is 20, this is 21. And is on the, okay, so theta. So I need to find sine theta and cos theta. Sine theta I know is opposite over hypotenuse, right? Opposite meaning the 21. Right? And then cos theta is going to be adjacent over hypotenuse. So this is opposite over hypotenuse. This is adjacent over hypotenuse. All right, well, I have opposite, I have adjacent, I don't have hypotenuse. How do you think I can find? Exactly, use Pythagorean theorem. Right, 20, 21. Okay, so 20 squared plus 21 squared. Okay, so that's a Pythagorean triplet. Okay, so that's a good one, 20, 21. And have I talked about Pythagorean triplets before? Yeah, okay. Yeah, so Pythagorean triplet is just whole numbers. It's just good numbers. The first one is 3, 4, 5. So I only know 2 of them. I know 3, 4, 5. I know 5, 12, 13. So these are the whole number Pythagorean theorem. Sometimes it's good to know the 3, 4, 5. It might help you speed up some problems. Anyway, so you know that the hypotenuse has got to be 29, so you can go ahead and actually solve for me. Mine's lagging a little bit. Sine theta is opposite over hypotenuse, so it's going to be 21 over 29. Okay, so this is the most basic, and I'll show you how. 46.4. And that's what we expected, 46.4. I expect it to be close to 45 because if the opposite and the adjacent is the same, that's an isosceles triangle, so that should be a 45. And this is quite close to the 45, so I'm happy with that result. And then cos theta equals the adjacent over hypotenuse. Yeah, also 40. Wait, what? Yeah. It would be that 46 point. Oh, you calculated the actual angle. That's why. Yeah, I didn't want the theta angle. Yeah. I just wanted the sine ratio. So the sine ratio is just going to be 21 over 29. Yeah, so no need to divide them. Yeah, so it depends if your teacher wanted divided or just leave it as a fraction then. Okay, so that's the third kind of problem. So now sometimes they might not actually give you the right coordinates. So let's actually do this. And actually I'll get you to do tan as well probably. So I'm going to do the exact same problem. This time I'm going to change up some things. I'm going to change two things actually. So I'm going to change up the coordinate. It's going to be -3, -4. And I want sine theta, cos theta, and tan theta. Okay. So for this kind of problem, even if you don't draw in the circle, I'd encourage you. Okay. It's 5? Yeah. The tan. Yeah. Yeah, so I'd encourage you to draw out something like this. So 3 and 4 is probably going to, 3 and 4 is going to look like this. All right, you got the 3, so -3, yeah. -3, -4 like that. Oh. All right, probably drew it a little backwards. Probably like this might be better. Yeah. -3, -4. Okay, so you told me already the hypotenuse works out to be 5. Yep. So the thing with these kind of problems, you should find out the hypotenuse. And then, so if you want sine theta, be careful this time because you're only looking for beta right here if you're doing the exact solutions. Yeah, but here's the thing. If you actually use the negative numbers when you do that, you will find theta right away. Yeah, you'll find theta right away. Yeah, if you're using the positive versions for this -4 and -3, then you're looking for beta. Yeah. So I would encourage you probably just go right straight to the answer. So sine theta. Again, we're not looking for that. So this is beta, that's theta. So again, we're not looking for the angle. I mean, they could ask you for angle, but we're really just interested in the ratio. So sine ratio is going to be -4 over 5. And as expected, it is negative because this is in the CAST T unit. I mean T quadrant. Yep. -3 over 5. And then lastly, careful with the 3 over 4. It's opposite over adjacent, not adjacent over opposite. Yep, exactly. Yep, there you go. All right. So now one more thing I'm going to throw in the mix is your reciprocal functions. So cosecant is, and this is not too difficult. Cosecant theta is really just cosecant theta is really just 1 over sine theta. So I don't know why cosecant pairs with sine, because cosecant sounds like it's more like cosine to me, but it's the opposite. Okay. And then secant, which sounds like sine, is actually 1 over cos theta. And then, yeah, have you heard of these ones yet? Yeah, so you are covering them. Okay, and then cotangent is cos theta over sine theta. Okay, and actually, no, I should not tell you that right away. I should not have told you that right away. Actually, I will go a little bit further down, because I should write that as 1 over tan theta first. And then because tan theta is sine over cos, therefore 1 over that is cos over tan. Yeah, sine. So that might, whoa, this guy went really far. Okay. So I should write an intermediate line. So that's 1 over tan theta. So therefore, if tan theta is sine over cosine, so that's why it's cosine over sine. But basically, yeah, you just got to know this is a reciprocal. It just means 1 over something. So first perspective is this. First perspective is the fact that, well, if cosecant is 1 over sine, that necessarily means that cosecant is also equals to hypotenuse over opposite. Because if one is opposite over hypotenuse, one is hypotenuse over opposite. Secant theta, therefore, is going to be hypotenuse over adjacent. And then cotangent theta, therefore, is going to be adjacent over opposite. Yeah, because it used to be opposite over adjacent. Now it's adjacent over over opposite. So each of these problems can be the 3 problems that I discussed earlier. You can throw in reciprocal function in the mix. For example, that last one, we could have asked you to not just list the sine theta, cos theta, tan theta, but also cosecant theta, secant theta, and cotangent theta. Yeah. So cosecant theta in the last problem would end up being, yeah, exactly, just negative 5 over 4. So you can either read that off from the sine theta and just flip it, or you can go straight from the triangle, which is what I actually want you to do in that exercise. So to recognize that, yeah, so go straight to the triangle, be like, hey, cosecant theta is really hypotenuse over opposite. And you should get that in your head too, just as fast as the sine, cosine, and tangent. Yeah. But if not, you can always, the other perspective, you go with the original perspective, which is find the sine first and then flip it. Yeah, whichever works for you, whichever works better. But the quadrant wise, it will still be the same. So that's still going to be a negative quadrant. So if it's a negative quadrant for sine, it's going to be a negative quadrant for cosecant. So now let's look at the first 2 types of problems. So the first type of problem was like, given the x, find the y. So perhaps I have cosecant this time of, let's do, I don't know, 240. Okay? So this is your first move. First move, I don't like seeing this. Cosecant, what the hell is cosecant? I don't know what that is. But I do know that this is 1 over sine of something. So I'm going to write this as 1 over sine of 240. Okay, once you get to here, everything solves as it was before. Basically, you solve what sine 240 was going to be equal to. And whatever that fraction, you're going to 1 over it. Or if you solved it in terms of decimals, you're going to do 1 over that. So I guess we can quickly finish that. Sine 240 is the same thing as saying 1 over, well, this is in the negative quadrant this time, right? This is in the 240 is in the negative quadrant. So I'm basically saying, well, if I can figure out what the beta is, then I know that's just the negative of that sine of that beta version. So I know the beta in this case is going to, yeah, 60. So this is going to be, I replace that with what? Yeah. So sine 240. Yeah, it's negative. It's in a negative quadrant, right? Oh, okay. So you skip one step ahead of me already, but I'm gonna write that as 1 over sine 60 first. Negative sine 60. So wait, you said it was root 3 over 2, right? Negative root 3 over 2. Yeah, so it's gonna be negative 2 over root 3, but you know to rationalize, yeah. Negative 2 root 3 over 3. All right. All right, so that brings us to the break, but you know, if you finish your break a little earlier, feel free to work on this one. Maybe secant theta is equals to negative negative 2. Yeah, negative 2 if that shows up. Okay. Alright, there we go. Negative 2. And then the other problem will be the other flavor. So maybe cotangent of I don't know, 750. Negative 750. Let's make it a little harder. Negative. Alright, I'll see you in about 7 to 8 minutes. Sure. Hey, Vera. Vera. Hey. All right. So did you get that? Okay, so the negative 750. You kept adding 360. Yep, it's 330. And you said it equals to negative. Did you write something there? Maybe it didn't update for me. I just saw you leaving it as negative 10. I saw 1 over negative 10. Oh, okay. So you did. Yeah. Sometimes you write it, it doesn't update for me. So what you want to write is the beta. Yeah, because you're saying it's equal to, because magnitude wise it's equals to this one, is what you're saying. But it's the negative version of that one. Yeah. Then once you figure out what the 1030 would be, yeah. Ten thirty is the 1030 1 over root 3. Let me see. So this one is gotta be root 3 over 2 and 1/2. So if you divide this one over 2, yeah, you're right. 1 over root 3. Exactly. And there you go. Yep. So I would. Yeah. So I would. Yeah, I would. Yeah, I would 1 over both of them. Yeah, because let's say so we're allowed to square both sides, right? I said. Sorry. You're allowed to square both sides, right? Square both sides. No. Are you allowed to square both sides? You're allowed to like in an equation, not here, like any equation. You're allowed to square both sides. That's a valid move. So here, what I'm saying is instead of squaring both sides, I'm taking both sides to the negative 1. That's basically what you're doing. Yeah. So you are allowed to flip both sides. Because when you're flipping both sides, it's essentially taking both sides to the negative 1. Yeah. So that's what you would get. Actually, no. Sorry. Well, you would not get that actually. Yeah, it'll be like 1 over 2 is flipping. Yeah, it'll be cos theta equals to negative 1/2. Yeah. Because then it basically means you flip one but not the other. Because if you leave it as 1 over cosine, that is what secant theta is equal to. Yeah. 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 So remember. Yeah, because remember, I look for the beta first, right? I don't really care. I just consider that as a positive. So I'm basically whoops. I'm basically gonna say that beta. So in the first quadrant, what will give me half? Yeah, and I think 60. It goes lower and lower, right? Beta 60. So yeah. So if beta 60, then you can go to the quadrants you want for the negatives. That is CAST, yep. 180 minus that and 180 plus that. Okay. What do you think? Do you think we should keep working on math, or do you think we should jump over to physics? Well, which one has a test coming up, or is more urgent? Okay, so I guess we can talk about a little bit of physics then, because the next thing I will probably get into is the graphing and introduce you to identities. So might as well just digest these and just keep working on them. So you know the 3 types of problems already. You can probably find them. But before I move on over, I kind of want to share my screen and show you one last thing I wanted to show you. So I won't get to in terms of graphing, but I want to make that connection so you can start thinking about that. All right, so let me know when you can see my screen. All right, so this is that unit circle we're talking about. Don't worry about the graph on the right side. Just know, this is what I'm saying here is, you know, the green and the blue is basically same thing as representing its coordinates. So you know that at this starting position at 0 degree, my y coordinate is 0 and my x coordinate is 1. And that corresponds to sine theta and cos theta, right? So you got sine theta as 0, cos theta as 1. At 90, it's going to be like this. Okay, 180. So now we can start looking at the how that relates to the graphs. So we can look at the green graph first, because right now I'm basically plotting on the y-axis what is that y direction, because the y direction corresponds to the sine theta, right, where sine is equals to. And then the x-axis is the angle at which I'm opening up this. So 360 would be a one whole circle. Okay, so let's see what happens. As I'm opening up this angle, I'm gonna see the green approaching from 0 to 90. But the curve there indicates that it's a decreasing rate. So the slope is getting smaller and smaller, and that's because, look, the first, if I go the first, let's say 10 degrees, first 10 degrees only gain me about 0.174. But the next 10 degrees, let's do 20 to be more dramatic actually. So the first 20 degrees went up by 0.342. That's a huge change, right? That's a pretty big change. 0.3. So we're like almost 1/3 of the way. Actually, a little past 1/3 of the way, because 1/3 would be 0.33. The next 20 degrees, the next 20 degree only went from 0.33 to 0.65. Sorry, 0.34. Exactly, because of the curving. So you know the chunk, let's say if you split that into 30s, it'll be even more, right, dramatic. Look, 30 degrees, I already went up 0.5 already. So that's already halfway there. And then the next 30, and then the next 30. So you see the last 30 is barely any change in the y direction. That's why when you connect these dots, trying to make sure at the zeros, you are crossing them at a perfect slope of 1, and that's actually what they are. So this would be +1 at 0, and then -1 at 180. I know you haven't talked about calculus yet, so you haven't, but in physics you talk about instantaneous slope, so tangent lines should not be that new to you. And then at the maximums and minimums, so the 1 and the -1s, they're flat. Okay, so now let's look at cosine. Cosine though starts at 1, and it will be decreasing to 0. And actually this time it's going to be the opposite. You start off slow, because this time let's look at the x direction. We'll look at the x direction this time. So because of the curvature of that circle, the first 30 degrees, the change in the x direction is not actually that great. Okay, and then the next 30, see the last 30 degrees, that's when we're gonna have the most changes in terms of the x direction. Okay, so that's the slope there. Reaches the 0, then it goes to negative, stays negative, 0, and then coming back to positive. Now tan is the weird one I'll probably cover last, so we'll learn how to do all the translation on the sine and cosine. But tangent's a bit weird. Look at what tangent is at 0 degree. At 0 degree, we are dividing 0 by 1. That's a value. 0 by 1 is 0. So that's why you see it starts at 0, just like sine theta. But let's see what happens at 90. At 90, you actually have a 1 divided by 0 this time, which is undefined, which means we have an asymptote, because we saw it before. When that number at the bottom does not get cancelled at the top, that's an asymptote. If it gets cancelled top and bottom, that's a hole. So this is a vertical asymptote. We're getting closer and closer to it, because imagine, this is talking about the ratio of the green to blue. Ratio of the green to blue at very, very close to 90, you're going to have a very big number, right, divided by a very small number. And then at these angles, the one close to 0 and 180, you have a very small number divided by a very big number. In that case, those would give you close to 0. Okay? One last thing is that the tangent has two. The period of tangent is 180, whereas the period of sine and cosine is 360. What that means is this. Sine and cosine repeats every 360 degrees, right? We can see on the graph. If we continue this pattern, it's like this sinusoidal shape. Sinusoidal shape is just a fancy way of saying this shape right here. That looks like a sine. So in reality, if you look at this closely, sine and cosine is really the same shape. One is just translated left and right relative to the other one. Right? If you shift the blue graph towards the right by 90 degrees, you realize they overlap. It's the exact same thing. Yeah, so that part might not be apparent to you. Maybe I'll show you that part on Desmo. Okay, I know I'm throwing a lot of things at you. If you caught like half of that, that's good. So if I look at Desmo, so what I'm talking about right now is the relationship between sine and cosine in terms of the graph. So I know I said I wasn't going to cover graphing, but I actually covered quite a bit. So sine x looks like this. Cosine x looks like this. Okay, so this is the last thing I'm going to say about it. If you shift the cosine graph by the right by 90, and that's going into the x and adding and subtracting, that's shifting left and right, right? Specifically, if I want to shift to the right by 90, it'll be minus. Right, I got to change something real quick, because right now we're in radians. Does your teacher cover radian? Okay, that's good then. That means you can learn everything in degree first, then you can transfer over to radian. So x-axis, we're going to go with negative 360 to 360. Y-axis, we can go with negative 1 to positive 1, and we'll go with degrees. Alright, there we go. So cos theta is still like that. If I subtract by 90, which is shifting it to the right, you see it ends up being the exact same graph. Yeah. All right. So that's just to illustrate to you they have the same shape, but tangent obviously don't have the same shape. Okay. So the last thing I'm gonna say is the tangent repeats every 180. So if you look at this, from one asymptote, so the 90-degree asymptote to 270-degree asymptote, that illustrates the whole of the shape of the tan. So the tan shape, this is the tan shape that looks like this. Well, you can see it repeats, because if you connect 270 to 360, if I continue that, that's basically the part from 0 to 90. So you can see that repeats every 180. So that's just to tell you the period of tangent is 180. The period of cosine and sine is going to be 360. All right, so that's all I'm going to say about that for today. Let's get into the physics now. Do you have, can you tell me how far are you? So what have you learned? Okay. All right, so let's, so I guess I'll just teach. Energy, it's not something you can touch, you know? But it's really something that gives us a way to calculate things that we can see. things that we can imply. Specifically, my definition of energy is just something that allows you to do work. Allows you to do work. So, first thing they should cover in this energy unit is what is work. Okay, two perspectives of work. One, work is equals to the amount of force applied in a certain direction. Just wait for my pen a little bit. It's lagging really hard. Let's see what can I do about that. Close up some things. Okay, it's back. So, work, and you're gonna have some calculations dealing with this. Oh, make your window a little bit bigger if you can. I have a little more work too. Or maybe you're more crowded to the left side. No. Yeah. Okay. Yeah. There you go. So work is gonna be equals to force parallel. So the component of the force that's pointing towards where where it's actually traveling, times its displacement. So what that means is this: if I have a box and I'm pushing it this way. Oh, by the way, for that last problem, I've thought about it. Adding is probably the way to go, because the way to think about that is, if this is my scale for this, if I'm pulling on that, then it's almost like that tension is gonna be registering as something that's higher than what it would have been if I didn't pull it. Okay. Yeah, and so if I push this with a force of 10 Newton, with the force of 10 Newton, and then this box traveled, let's say 5 meters, and that whole time you were applying force. So you have to be applying force the whole time. So you're still applying force of 10 Newton. So then we can calculate that the work being done in this scenario. So they're saying the work being done after pushing that for a whole 5 meters is going to be equals to force parallel. So it is parallel to that direction, and I'll show you the next example where it's not parallel. We're gonna find that 10 times 5, we're gonna get 50. So in this case, work is gonna be 50. And let's figure out what the unit is. What's the unit of force? Oh yeah, well, work is gonna be joules, but we have a different unit right now, which will be equals to joules. So if we just investigate what we multiplied just now, we multiplied a Newton by meter. So work can have two units. Work can have Newton meter. So this is in either Newton meter, which is the same thing as joules. So joules and Newton meters are actually the same unit. Okay, just like how Newton is the same thing as meters per second kilogram, right? Okay. All right, so now let's look at what happens if I'm pushing down at an angle. So this time I'm pushing this box down at an angle. Still 10 Newton. So that's why now you're gonna know the most efficient way to push the box is parallel to it. Well, I guess we kind of knew that already. Right, if you want to push something, you're always trying to get down to its level and trying to push it as straight as we can, right? Because that is the most efficient way of doing things. All right, so in this case, still traveled 5 meters. So I still traveled 5 meters, and constantly I'm applying this Newton, a 10 Newton of force, and let me just write that is going to be 30 degrees towards the horizontal. So it's going to be 30 degrees applied to horizontal. So again, work is still force times displacement, but as I said, it needs to be the force that's parallel to my motion. So yeah, exactly. This time we're going to do cosine. So you know the shortcut. We're just going to... Yeah. Well, yeah, no matter sine or cosine, you know the component is always going to be less than the original. Yeah, so this, we're going to have cos 30 times 10 and then times 5. Yeah, so you see, it's going to be less work being done on here. Yeah, so 43.3, right? Okay, so that's the first perspective. So that's the work. So that's one perspective of work. And now I'll tell you how work relates to energy. Because this is the connection point. Work is basically the connection point between your energy chapter and your kinematics chapter. Because you can see, with the work, we can convert from energy into the realm of the delta D, which will give you some kind of meters, and then you can probably work from there in terms of getting into the kinematics equations, accelerations and all that. So force, so this work is going to be 43.3. Okay, so the other perspective is this. And now I can actually talk a little bit more about energy. Everything has energy in it, but in physics, we reduce them down into two main types of energy. Okay, in physics. And I'll tell you the one that they've neglected. Okay. So everything has energy, but if we look at a macro object as a whole, so let's say you're looking at yourself as a whole. So yourself can be reduced down to a point object. So you as a whole has two main type of energy. Your energy total is equals to your kinetic energy. So how fast you're traveling. And actually, not just how fast you're traveling. You realize kinetic energy is not just talking about translational energy, but two other things: rotational energy and vibrational energy. So when we learn gases in a container, for example, when we thought of, in the gas unit last year, maybe if you learned gas, they're all in random motion, and then you learned about the pressure and volume and all that, right? Did you learn that in chemistry? Yeah, a little bit. So they all possess kinetic energy, right? And the average kinetic energy is really corresponding to their temperature, right? Because high temperature really just means the air molecule, when it's hot outside, it just means the air molecules are moving a lot faster. But when it's cold outside, the air molecules are going a lot slower. But when you talk about the kinetic energy, I know in our head, right away we go to them moving around. That's kinetic energy. They're moving around. But them just rotating, spinning around on its own axis, and them vibrating, that's also kinetic energy as well. So when you talk about your kinetic energy, I'm not just talking about you moving. I'm also talking about the molecules inside you vibrating and all that. So that kind of relates to heat in a way. Okay? But I'm not going to write that as heat. So kinetic energy, but in the context of physics, most likely we're basically talking about that translation though. So plus potential energy. Potential energy. And specifically, we're going to be talking about, if we're talking about point source, so just an object reduced down to a point, we're talking about gravitational potential energy. And I'll explain what that is. Gravitational potential energy. Okay, so kinetic energy is easy to understand. Gravitational potential energy, well, any kind of potential energy, we're talking about the potential to do work. It means this. For example, if I put in work, okay, to raise this calculator, I'm putting in work, right? Because I know I was pushing sideways last time in the last example, but I can do work upside too. Because look, I'm applying a force for it to go up, right? A normal force for it to go up. And the displacement is actually going the same direction. So I am putting in some amount of work. So that work can actually be translated into a kinetic energy when I release my hand. Because as soon as I release this, what's the calculator going to do? It's going to fall down. So I've created some potential energy, right? By putting in some work, I've gained the potential for it to have some kinetic energy as it falls down. That's potential energy. And so because, well, how far does it fall? Right? Where's the ground? What is the ground? Is the ground the ground in my living room? Is the ground outside? Where's the ground? Is the ground, it really depends on where you are. So what I'm trying to say is energy, and specifically in this case, gravitational potential energy, everything isn't relative. I mean, even kinetic energy could be relative, right? We're all moving right now, technically. It depends on what the frame of reference is, right? If you're standing out of space, we're actually moving quite fast. Right? If you're standing beside me, then I haven't been moving that much. Not since the quarantine started. So, each of them are relative to the other. Kinetic energy, usually we're dealing with on Earth, right? There's not going to be too much frame of reference. So most likely, kinetic energy is going to be straightforward. But gravitational potential energy, you need to define where the zero mark is for the height. Okay? So this is what I mean. And we can actually use this to solve a most simple type of problem. Let's actually solve the one with my calculator. So my calculator was moved up. Let's say I raised my calculator up. So I'm saying that my table is the ground right now, because I always need to define where's the height of zero. So my ground of my table is the height of zero. I have moved my book up by, let's say, 5 meters. Okay, and I just left it there. Okay, so right now I can calculate the energy total at the top. Okay, and I must actually, probably, if we're talking about energy, I should tell you the first rule of energy first. And that relates to thermodynamics. First rule says this: energy cannot be created or destroyed. Okay, energy cannot be created or destroyed, which means this: unless you have lost energy somewhere, and sometimes you can lose energy, but most of the problems we're going to deal with this year, we're going to ignore the loss of energy. What can lose energy? Friction, right? Heat, right? Any useless, I wouldn't say useless, sorry, non-conservative forces. We'll discuss that in a second. But right now, let's just say energy is conserved, so no loss of energy. Then energy must be the same before and after. The energy that this calculator has at the top here must be the same at the bottom after I have released it. So at the top, let's calculate. At the top, my energy, again, energy is always going to be EK, which is kinetic energy, plus EP, which is potential energy. Well, at the top, what kind of speed does it have? It got no speed. It got no speed, so it's zero. But it has some kind of potential energy. So I realized I should probably give you the equations for them as well. So this one you just have to memorize. I'll derive them for you later if you find that will be useful. But I doubt we need to derive them for high school. So kinetic energy is going to be half mv squared. Okay, and if you need to derive them, they basically come from kinematic equations. Actually, I should say the other way around. The kinetic equation can be derived from this. I don't know which way is which, but you can derive one from the other if you start with one. Yeah, half mv squared. So that's kinetic energy. Gravitational energy is even easier. It's just mgh. Okay, so let's look at all these quantities. So kinetic energy, it means if you know the mass of something, if you know the velocity of something, you know the kinetic energy. Right, because it's just half m times v squared. The bigger the mass, the more kinetic energy. Think about a train going at 5 meters per second versus my bike going to 5 meters per second. I think you'd rather get hit by my bike going 5 meters per second because it would have less kinetic energy. And if it has less kinetic energy, it can do less work on you. Less work on you means less internal damage to your organs. And then velocity, that one's easy. The faster it is, the more energy you'll possess. You'd rather get hit by a 10 meters per second tennis ball than 100 meters per second tennis ball. Okay. Potential energy, mgh. M is the mass, g is gravity, h is height. See, I don't even bother writing any of these down because the letters are pretty straightforward for you. Mass, the higher the mass, the more potential it has to gain energy. Because you can think about that. When I drop that, the heavier it is, the more energy it's going to gain. Okay. That's not to say it's going to be faster though, because I hope you know that by now, that when you drop, have you seen the experiment with them dropping a bowling ball and the feather in outer space? They drop at the same time, right? So it's not to say something heavier is faster, but I'm saying heavier has more mass, so when you plug it back into the half mv squared, it's going to be bigger. Height, the higher you pull it up, the more potential energy it will be stored. So when you release it, the more kinetic energy, the more time it will have, or you can think about, to gain that speed. Okay, so back to my problem. At the top, I have 0. I mean, we could have solved that half mv squared, plug in the v as 0, then the whole thing would be 0. And then mgh, we do have mgh though. Again, mgh, it really depends on, this is all relative. It depends on where you set height as 0, right? Because if you set the top position as 0, then your height at the bottom will just be negative. Then you'll just calculate a negative energy, which could make sense because energy, we're always just looking relatively. You can never say absolute energy of something, okay? I don't know what your energy is, but relative to someone else, I can tell. Okay, so it's always in reference to something. Okay, so E total at the top, so that means E top, the total energy he has at the top is just equals to mgh, and we can get an actual value for that. So E total at the top, so E total at the top is going to be equals to the mass of him. I should probably give you a mass, sorry. How about, let's do 10 kilograms. Okay, it's going to be 10 kilograms times 9.81 times the height, which is 5 meters. Okay, make sure they're on SI units, right? Meters per second, meters, kg. So if we multiply all that together, we should get 490.5. Now, what happens after I release that? That's going to travel the whole 5 meters, slam on the ground, and that's it. Let's say it didn't make any noises, right? Because technically, as soon as I make a sound, some energy is lost. Because sound is energy, sound energy. So in this perfect physics world, there was no sound being made, nothing, no air friction, because as it's coming down, air friction, anytime there's friction or any sound loss, heat loss, there's actually a loss of energy there. So technically, if it's that air drag, so the air friction would have had some energy loss. But let's say there's no energy loss. At the bottom, what's the total energy going to be equal to? Yeah, no energy loss. Then it'll be the same thing, 490.5. So the E total at the bottom, so E total at the bottom is going to be 490.5. Oh, guess what? 490.5. What is that equals to? Again, it's going to be equals to EK plus EP. Okay. I know I haven't really given a question. There's not really a question. But now I'm going to give you a question because I'm just really looking at what's going on right now. But this is a classic problem to find out what is the speed at which it crashes onto the ground. So we can actually solve for that now. Because at the ground, what's the height at the ground? I've let it be 0. So EP is 0 because if I sub in H. So that's just EK, and EK is half mv squared, and I have m. I know my mass, so I can really plug in everything. Okay, this input is really bad today. Yeah, so you can give me that value. So 490.5 is equal to half mv squared. Okay, so V is going to be equals to 9.9. All right, I want you to do a quick kinematic equation because this is the energy perspective, but we learned a totally different method of solving this in kinetic chapter, right? Okay, so I want you to do that, and that'll be the last thing we do, and we're done. So we're going to set V1 as 0. V2 I don't know. Delta D is going to be 5. Acceleration is going to be 9.81. I'm letting down be positive right now. And I want you to solve for me V2, right? And I want you to convince yourself that both method gives you the right solution. Yeah, you tell me. You do this. Yeah. This is just a kinetics review. Is it 0? Well, you do it. So this is a problem. I have a book. It's 5 meters above the ground. Okay, I release it, drop to the ground. How fast is it going at the ground? Yeah, V1 is 0 because you're releasing it from rest. Depends. Yeah. You don't have a time now. I do have delta D though, and I do have acceleration, so that's 3 quantities already, right? 9.81, gravity. Okay, no pressure, but I expect you to know how to do this one. Yeah, of course, it's the same thing because, well, it shouldn't be different. Yeah, so it makes sense. So this is a valid way. So we've learned another way of dealing with some kinetic problem, dealing from the energy perspective. Okay, so I guess I'll wait for your text for the next lesson. Okay, yeah, so I will see you next time then. All right, no problem. See ya. Okay, you're gonna have to exit because I'm gonna keep this room for the next one. Hello, hello. All right, what are we working on today? Do you need the Zeitport link? Wait, is this even you? Why are we doing organic? Wait, this is not you. What was the last thing we did? Oh, okay. This is definitely not you. Why do I have Yuki written down? Okay, alright, doesn't matter. Yeah, you haven't done organic in a while. Yuki. Equilibrium? Okay, I'm just gonna open this one up. I'm just gonna invite you onto here. Alright, so wait, you said acid and base, right? Yeah. We're on the acid and base chapter. Any questions to start? You fix up their sleep schedule a little bit. That is quite an improvement. And the sunlight's coming up sooner and sooner too. It's like yeah, that's the alarm clock nowadays, huh? The sun's up, we gotta sleep. Yeah, exactly. Okay. Mm-hmm. You tell me, can you do one problem? So for example, let's do this problem right here. Oh, let's stop. Okay, to the bottom. Yeah. Well, you gotta show me you know how to do it. You mean I did it? Okay, don't move for now. Okay, okay. So show me that you can do it. Okay, all right. Next. You're not gonna remember from what we did last time. I don't believe you. No. Okay. Okay, then show me the steps. Tell me the steps. What do I do first? If I need to find a concentration here. I send you the Zeitboard link. No, I didn't. Yeah, I did. I put it on the chat. Here, I'll copy that one more time. On the Zoom chat. The pH. What's up? Yeah, actually, yeah, this one is definitely worth doing. I don't know if we covered polyprotic. Do you know? Do you even know what polyprotic means? Yeah, kind of go with the words. I think you can figure it out. Poly means proton. Sorry, protic means like some. Yeah, something that can give off more than one hydrogen, more than one proton. So polyprotic means you have more than one proton to dissociate. So something like HCl is a monoprotic because it only has one hydrogen. So something like this one, H3PO4, could be polyprotic because you have more than one. Did you have some quizzes you wanted to do or something? Okay. Yeah, can't talk about probably acid and base quiz first, because you really need to know your acid and base before we move on to salts. Because salts is kind of the product of a neutralization reaction, right? I thought all exams are cancelled in Ontario. Oh. Oh no. Okay. Or one of my students got COVID. No idea. It's I thought it's you people from Florida. No, no, I'm not even saying your age group, where you're from. Florida. Have you seen the people there? Alright. Oh, we're doing that one. Okay. Alright. Let's do that. Is it just me? Oh, okay. No, it's not just me. It's probably you too. Alright, and the reaction. Oh, is there only 3 problems? Okay. Yeah. So yeah, label so look at the equation. We've done this last time. So which one's the acid, which one's the base? Because remember, second definition, we're always reacting an acid with the base. Right? HCN is the acid. Perfect. Right. Okay, so conjugate acid and base are always a pair, and they always differ by 1 hydrogen. So if you need to verify that, they are different. Yeah, and then that must be the conjugate acid then. All right. Yeah, it's okay. Doesn't matter. Okay, find pH of each of the following. Say that again. Are you on the whiteboard? No, you are not on the whiteboard. I don't see you. I posted it on the Zoom chat. But doesn't matter. You don't need. I'm just talking. Just in case you want to revisit this as a practice or as a reference. Find the pH of the following. Okay. What's the pH of 0.015 HCl? So that requires you to remember what is a actually, come to think about it, you can probably deduce this. You don't have to make a calculation. I'm gonna have to, how about this? You have to show me calculation for only 2 of them. And that is going to be the how about carbonic acid and the F minus. So number 4 and 5, I need you to actually find, show me calculation. But before that, can you guess? Because I think you can guess a lot of them already. Can you? Yeah. For number 1, you can guess number 1. I'm pretty sure 0.015 molar of HCl. Okay. Looking at all the numbers, even You can probably guess what that is, but if you can't, then I'm gonna get you to do it the full way. Yeah. I would go with the smallest one because just looking at, without even looking at the pHs on the left side, HCl, how many of these are acids? So how many of these do you expect to be lower than 7, first of all? 1 is going to be lower than 7. 3 is going to be lower than 7. And 4 is going to be lower than 7. Yeah, so let's see if there's 3 of them that's lower than 7. 1, 2, 3, we do see that. So we see 3.5, 1.8, and 3. Okay, so I know the HCl is the least concentrated, but I'm pretty confident that's still pretty close enough that that's going to be the lowest because HCl is a strong acid. How do we define strong acid again? What's the difference between strong and weak? Fully dissociates. 100% dissociation is something like strong acid. So that means with 0.015 molar, you're going to get 0.015 molar of H plus. Whereas something like acetic acid will be less. But we can verify that right away because if 0.015 molar is going to turn into 0.05, so you can just negative log 0.015. And indeed, it is 1.8. Okay? So with that logic, can you guess the most extreme? Which one do you expect to be most basic? Probably the NaOH. And it's probably going to be the exact same number, right? Because we're going to do negative log of the same number. So why isn't the pH the same? And that's because what we're calculating there is a pOH when you do a negative log of the 0.015 in this case. Because NaOH dissociates into Na plus and OH minus. And as I said, strong acid and base, you can just use the first definition of just dissociating between the two. So 1.8, yeah, so it's going to be 12. Roughly, yeah, that's the closest one. All right. So the other ones you probably will need to do some kind of calculation. So that's why I said if you just do one of them, then you can rule out, then you can just apply the other one, right? Because right now 3.5, 3.0, one of them's got to be acetic acid, one of them's got to be carbonic acid. So if you figure out which one's carbonic acid, you can just give acetic acid the other one. So that's why it seems like you have to do 6 calculations, but you don't. So I only want to see calculations done on number 4. And number 6 or 5, up to you. Number 5, let's say. So 4 and 5. Okay, yep, carbonic acid. What is it in the first place? Yeah, better be able to name that. Give the formula. So carbonic acid is putting hydrogen with who? Carbonate. Right. If it's just carbon, it'll be a binary acid. Binary acid, we do hydro something, right? So hydrocarbonic acid would be just H and the C. I don't think that's even that common, though. Never really seen that. H2CO3, because CO3 is a 2 minus. So then when you bring the 2 down, you get 2. No, just once. Technically, yes, twice. But the second one isn't really going to contribute much. I think just doing it once is going to get you close enough to the answer. The second deprotonation is so little, it contributes very little to the pH. Okay, so let's write the equation first. H2CO3, what am I adding it with? Water. And then what do I get as product? Okay, H3O3 minus. And H3O plus. Perfect. Okay, so I have those things. So now what do I do with them? Yeah, put it in a nice table. All right, so what do I write as the starting quantity for H2CO3, or the initial quantity? Okay, and then what are the initials for the HCO3 minus and the H3O plus? 0 and 0. What are the changes going to be? Yeah. Yep, good. And that's because the coefficients are all 1, 1, 1, 1, 1. And then, okay, so the final, I'm sure you know, you just put them together. 0.25 minus x. This one will be x, this one will be x. Okay, now what do I do? So you're going to look for a chart somewhere.
You're gonna find yourself a KA table. You have a go-to one, or are you just Googling nowadays? Oh, I think you are. Your internet dropped off. Okay, you're back. Maybe you're not. Are you back? Yes, you are. Where are you consulting this table? Are you going on the Google or? Okay, yeah. Yeah, just have a go-to. You know, you're in this acid and base chapter. Make sure you always have one of those charts handy. Yeah, what did you get for the KA? Yeah. Yeah, and I'll actually take it all the way. I'll teach you how to find the actual precise pH. I don't think it's necessary here because it should get you close enough. The second deprotonation, I don't expect it to change more than 0.01 with the pH. Yeah, so that's pretty low already. Okay, might as well give me the pKa2. Can you see that anywhere? pKa2. So the second pKa. So sometimes they list it as a chart. So for the polyprotic, they put them all together. So you have pKa, pKa2. Sometimes you have to find it in terms of the HCO3. So the Ka2 is relative to the HCO3 minus, right? So do you see a Ka value for HCO3 minus turning into CO3 2 minus? Or if you have the Kb of CO3 2 minus, that works too, because you can just do Kw divided by of CO3 minus, 2 minus, so carbonate. Wait, Kb for CO3 2 minus, right? You said is what? What is it? So do you understand why that helps me? Okay, go to the Zeitboard real quick. I'm going to show you. If I write this as the base, CO2 minus, the CO3 2 minus, what am I adding it with? H2O. Oh yeah, you gotta open up the Zeitboard. Oh, maybe close up some tabs first. Ooh. Oh, that must be high altitude sickness research. How's that coming along? Oh, you gotta make a video. Ooh. Yeah. No. MG. Okay. Let me look up. Maybe I'll find that. Let's see if we. Okay, because I think we have like 2 or 3 boards open right now. Yuki equilibrium. No. Yuki, maybe this one. Let's see. March 31st, 2020. Did you click on the link I gave you on Zoom? And that's the one that brought you to? Huh. Okay, let me see. No, you're not on here. Okay, I'm just gonna open up a new one. I feel like I always open up new ones with you. No. What do you see as the last thing? Oh, okay. Let me go back to that one then. UK, equilibrium there. Okay, yeah, I see you. Yuki Isabel 20. Alright, yeah, so can you complete that equation on the left here? So I'm showing you why. So right now I'm trying to find this. So what I'm talking about KA2. Do you know what I'm saying by KA2? Do you know what I'm saying when I say KA2? KA2 means this. Right after you deprotonate the first time, you're gonna left with HCO3 minus. And the initial amount is basically the final amount of after the first time you do it. So this is relating to that polyprotic problem that I told you earlier. As I said, you don't need to do that for this one because I think doing it the first time should get you close enough to the answer that you need already. Okay, but if I continue writing this though, I get HCO3 minus plus H2O, giving me CO32 minus plus H3O plus. Oh gosh. So this was supposed to be HCO3 minus H2O, giving me CO32 minus and H3O plus. So that's what I mean. I need to know the Ka value for this. If you're saying the book didn't give it to you, another way we can do it is find the reverse of this. Because what I'm saying is if you know the Kb of CO3 2 minus, which is the exact opposite of this equation pretty much. Pretty much, not exactly. But if you know the Kb for this, which is 2.1 times 10 to the negative 4, then I know Ka has got to be 10 to the negative 14 divided by that. You know that equation, right? Where Ka times Kb equals to Kw. I talked about that in the auto-ionization of water. So that means if you know the Ka, for example, if I wanted to know the Kb of HCO3 minus, then I can just, find the reverse of this. Okay, so what I'm saying here is the Ka in this case is going to be 10 to the negative 14 divided by 2.1 times 10 to the negative 4, which is going to be quite small. 10 to the negative 14 divided by 2.1 times 10 to the negative 4. So that's 4.76 times 10 to the negative 11. Okay. Oh, that's just a truth. Like that's just an equation you need to know. It's like saying why is pH plus pOH equals to 14. That's the exact same question. Yeah. So Ka times Kb. So the conjugate acid with its conjugate base pair, the Ka and Kb values, they multiply to be a constant Kw. And Kw is 10 to the negative 14. This comes from the it's actually an experimental result. They measure that experimentally by measuring. Yeah, so this is basically an equation that helps you convert between Ka and Kb. So this is Ka2. So don't worry about using this. As I said, you don't really even need to do this part because we didn't need to know that precisely about the pH of this. But we're going to go that precisely so you know how to answer that problem. So, okay, you can do the first part of this first. So the Ka1, 4.2 times 10 to the negative 7. What am I doing with that?
Are you calculating it already? So you're gonna have x squared. Are you using the 500? Oh, did you find out what rule are we using? Was it 100, 500, or 1,000? Oh, okay. Okay, but did I discuss that last time with the shortcuts? Yeah, so if you divide the initial concentration by the Ka, in this case, doesn't matter if 500 or 1,000, it's going to cover that, so you can reduce the 0.25 minus x just straight to a 0.25. Wait, give me 1 second. 42 negative 7 times 0.25 and then square root it. Wait, what did you say x was again? Yep, that's what I got. Perfect. Okay, that's the moles per liter. Okay, as I said, you can pretty much stop from here, right? Because you already found the H3O plus concentration here. Because that's equals to x, so you're going to do negative log of that answer. And you're going to get that's 3.48. So that's close enough to 3.5. But I'm here to tell you it's probably a little bit less than that. And that's because that's not done yet. The HCO3 minus can actually further deprotonate the second time. Right? It still has a proton to give. And it's going to be given in terms of this equation here. Okay, so I'm going to take over from here. So, you looking at the Zeitboard? Okay, so this time, the initial, how much do I start with the HCO3 minus? I started from the final amount from that last deprotonation event. So I know I'm starting off with 3.24. So that's why I say this can pretty much be ignored. Because look, this already starts off very tiny. And on top of that, the Ka is very tiny. So not only do you have a small concentration to begin with already, but very small part of that concentration is actually going to break apart to give you more H3O. Okay, but anyways, we can go with this. So CO3 2 minus, well, you don't have any of those yet. You still haven't made any of that. So that's going to be 0. But what about H3O plus? What's the initial amount for H3O plus? What's the initial? What should I put it in the I column of H3O plus? Yeah, well, that's how much was made previously. So the ending part, so the ending concentration of that first deprotonation event is going to be your initial part, which is also 3.24 times 10 to the negative 4. Because the x you calculated basically applies to both the HCO3 minus and H3O plus. Do you understand that part? Okay. So now, still the same thing. I'm going to minus x. I'm going to plus x. I'm going to minus x. Okay, so I have 3.24 times 10 to the negative 4 minus x. I have 3.24 times 10 to the minus 4 plus x. And then I have x over here. Okay, so let's do a quick check to see if we can do the 100 rule or 500 rule or whichever. So in this case, I'm going to be dividing 3.24 to the power of negative 4. Divide that by 4.76 to the power of negative 11. So probably is doable. Yeah, that's going to be 6 million. So we can definitely do the 100 rule or 1,000 rule. So equals to x times 3.24 times 10 to the negative 4. That's going to be plus x, but we know we're going to reduce that. And then at the bottom here we have 3.24 times 10 to the negative 14. Not 14, 4 minus x. So look, the shortcut means that this one I can just ignore the plus x. This one I can ignore the minus x. So they're basically the same thing. So x in the end is finally going to be, x is going to be 4.76
times 10 to the negative 11. What do I want? I want the H3O plus concentration. This is what I mean. That's why I said it's not really necessary for this one specifically, because the Ka2 is so small. Look, if I add 3.24 times 10 to the negative 4, if I add that with 4.76, it probably doesn't even make it onto the significant digits. Okay, but I'm going to make that addition anyways. 3.24 times 10 to the negative 4 plus 4.76. 10 to the negative 11. That's going to be added up to be 3.24, still 3.24, 0.000476. So the 476 get added on way later. Do you know what I'm saying? Yeah. So then if I do a negative log pH of that, it's probably going to be very similar to that one we got previously. So I'm going to get 3.24 0.000476, and then if I go ahead, oh, that's times 10 to the negative 4 still. So if I do negative log of that answer, pH is going to be 3.489, which is exact same as what we got last time. So that's what I'm saying about the protonation event being very slow. Okay, so you can fill that in there. So the so that's going to be 4. Okay, so the last two, okay, so we can probably go a little bit faster with this one. Which one do you want to do? Do you want to do the fluorine or do you want to do the Cn minus? Okay. So let's do the F minus. Can you just give me the Kb value of that? And what happens if you can't find a Kb? You can find the Ka of what and then calculate from there. Oh, so they do have one. 1.4 times 10 to the negative 11. So if you found a chart that doesn't have that, then you would need to find the Ka of its conjugate acid, which is HF, and then do 10 to the negative 14 divided by whatever that Ka is. But since you know it right away, it's 1.4, you said, times 10 to the negative 11. Okay, so that's going to be equals to, so I'm not even going to build this ice table because I know where it's going, right? You're going to have x squared, right, on the right side. And then on the left side, you don't include the H2O. So it's going to be your initial concentration minus x, so 0.15. Okay, so this is just me visualizing an ice table in my head, so you can probably take the extra time to write that out. And pretty clearly we can do the 1000 rule because 0.15 divided by 10 to the negative 11, that's a huge gap there. Alright, and then let me know the x value once you get that. Oh, and actually you gotta be careful in terms of writing pH though. So tell me what you get x first. Yeah, that's what I got too. And then, are you calculating, when you negative log that, are you calculating POH or pH? Exactly. Please don't forget about that because people make that mistake all the time. They just think negative log, oh, I'm not going to look for a pH. and then you just get the first answer they take. They say, oh, it's 5.84, and they go look on the answer chart. Oh, that's not one of the answers. What's wrong? Yep. Yeah, it's fine. We're just mostly practicing. Let's go to page 3. As long as I print screen that for 4 question. Okay, whoops. Okay, doesn't matter. I will paste down because these are not for marks, right? Yeah. Then we're good. Okay, let's go to the next question so I can make sure I copied that question down so we have that at least somewhere. Oh, we could just do it again. Okay, yeah, that works as well. Okay, so let's go to 3. All right, so what are you gonna do first? Identify an unknown weak monoproduct. A monoproduct, you know, it just means hexa aqua aluminum, aluminum with 6 hydrogens with it. You know what? Remember the dot hydrates? Yeah, I remember you did the nomen. Yeah. Although probably not that one probably. Carbonic acid, yeah, because it's a polyprotic acid. Yeah. Okay, yep, that's a good one. Yeah, but really, you know, I think what they want you to do is find out what the Ka is, right? Because if you can find out what the Ka is, then you can just consult the table, you know, who has the Ka of this. So I would begin by drawing in the equation. So you have some kind of HA, a known acid. You're gonna react it with H2O, giving you A minus and H3O plus. Right, HA is just gonna be a generic for some kind of acid. You can build an ice table, but really the important thing is when the concentration is 0.55. So where do we fill in for that 0.55? Which part does it go on our ice table? The initial for the HA, right? So it'll be 0.55 molar. The pH, where does that information go to? What are we gonna do with pH first? Probably do something with the calculator first. And that's to get the hydronium concentration. Because pH is basically a measure of how much hydronium you have or proton you have, right? H plus or H3O plus. In this case, what's the equation there to go from pH to concentration? So you know the forward rate, pH is equals to negative log of that. So you can either start with that and use your log skills to do that, or you can memorize the other equation, which is the fact that H3O plus ion, the concentration is equals to 10 to the power of negative pH. And it's going to be the same for OH. So if you have POH, then it will be OH minus is equals to 10 to the power of negative POH. Okay. So if you punch that into your calculator, you should get that the concentration of the hydronium, which you're going to put at the ending concentration, or the equilibrium concentration. I keep calling it the end, initial and the end, but I think that E is supposed to be equilibrium. So the equilibrium concentration is 2.089 times 10 to the negative 3. All right, so now what do we do from all this? No, I said that. Oh, that's the E column. You know the ICE, ICE table? The E column is the equilibrium concentrations. The I column is the initial concentration. No, this is H3O. Remember, so the last step, how did you find the pH? When you found the pH, did you find negative log of what the equilibrium concentration for HA is? No, you went to find out, well, what is the H3O plus concentration, and then you took the negative log of that, right? So this is kind of like the reverse. So you're given the pH, so you can find the final concentration of the H3O plus, or the equilibrium. Okay, so I'm going to fill in the rest. The initial is going to be 0 and 0 for the A minus and H3O plus. It's going to be minus X. It's going to be plus X. It's going to be plus X. So if I know this is plus X, this is plus X. So if I know the final concentration for H3O plus is going to be that, 2.089 times 10 to the negative 3, then I know that A minus is also 2.089 times 10 to the negative 3. And that means if I know what X is, I also know the equilibrium concentration of the HA, because that's just going to be 0.55 minus whatever that is, 2.089 power of negative 3. So that's going to be 0.5479. You understand what I did so far? Because how can I find a Ka value? The only way to find Ka value if I have the equilibrium concentration of everything. So what I'm saying is I first found the equilibrium concentration for H3O plus. Since that is equals to X, now I know what X is, then I can use that X to basically go to equilibrium concentration for everybody else. A minus is equals to X, so that's why I just straight up wrote down 2.089 times 10 to the negative 3. The HA, you need to do a little bit of more work because the equilibrium concentration is 0.55 minus X. Since I just found out what X is, just plug that in, 0.55 minus 2.089 times 10 to the negative 3. So now you understand where I got the 4 equilibrium. Oh, sorry, 3 equilibrium. So now what do? Yeah, plug it into the Ka value. Right, then we have 2.089 times 10 to the negative 3 times itself, so I'm just going to write square, over 0.5479. Did you get a number? What did you get? Alright, and then now you are going to check that against the table, probably specifically looking at acetic acid and hydrogen sulfide, and see which one. Actually, probably hydrogen sulfide. Because acetic acid is, I believe acetic acid should be 1.8 times 10 to the negative 5. That should be a value there. Oh, really? Oh, really? What, hydrogen sulfide? Okay. So maybe ignore the mono product. Because, can you check carbonic acid? Okay, let's check hexa aqua aluminum. So that should be showing up as Al dot 6H2O. Okay, let me try that one more time. 10 to the negative pH. 10 to the negative 2.68. Okay. I'll verify that. Hexa aqua. Yeah, I think that looks good. Yeah, hexa aqua aluminum. Yep, no problem. And I copied that down onto Ziteboard as well. Oh, there it is. A hexa. Oh, if you looked at the question number 4, it gave you the answer actually. Yeah, that's okay. So, but I mean, this problem will most likely show up as, hey, what's the Ka of this unknown acid? Okay, weak monoprotic acid when the concentration is 0.55 molar. pH is 2.68. Determine the Kb for its conjugate base. Oh, okay. I think you can get that one right there. How do we do that? What is its conjugate base anyways? Yeah. I mean, just write it at HA for now. So HA plus H2O give you H3O plus and A minus. Yep. So we're basically saying Kb of what? Sorry, say that one more time. Did I hear penta? Okay, you're getting cut off a little bit. But basically, we're looking for the Kb of this. I said earlier, not exactly like that, because it's a little more complicated, because we're not taking a whole hydrogen, water out. We're just taking a hydrogen out. So if we write this as that's like a coarse formula, AlH12O6, then we're basically saying the conjugate base is one less hydrogen from that. So AlH11O6, and then perhaps with some kind of negative charge, because we just lost a positive ion from that. Okay, but we don't really need to know the formula. That's not important here. What's important is, you still there? No, you're not there anymore. You got cut off. Oh, are you still there? Yeah. Okay, so the conjugate base of an acid, the relationship is, if they're a pairing, Ka and Kb multiplies to be Kw. Yeah, remember that? So if we know the Ka, which we actually solved from the last problem, 7.96 times 10 to the negative 6, we can just do Kb as 10 to the negative 14 divided by 7.96 times 10 to the negative 6. To the negative 14 divided by so it says use E to represent 10 and then probably 2 significant digits. because of the 0.55. So either if it's 3 sig figs 1.26 times 10 to the negative 9, or 1 sig fig 1.3 times 10 to the negative 9. And that is the KB. Yeah. Negative 9. Yeah. Yep, so you know what I'm saying with KA and KB relationship now. So if you know because sometimes you have to do this part, if the table that you're looking at doesn't give you a specific KA KB value, because sometimes, you know, to reduce redundancy, perhaps they don't give you. Okay, so I guess while you do this, you can do that during break. Let's take a 10-minute break. I'll see you back in 10 minutes, and then we can maybe get into salts if you're comfortable with this part already. All right. And maybe go like reset your modem, or I'll reset my modem or something, because it's kind of laggy. All right, I'll see you back after the break. You're still laggy. Can you hear me? You are frozen. Alright, I'm gonna get a buy first before I leave. Are you there? Yeah. We good? Okay, I'll see you in a break. Bye. Alright, and we are back. Okay, so I don't know if you got a chance to look through if there's anything else you need clarifying for acid and base, but if there is no more, then sorry, not acid and base. This whole thing is acid and base, but this whole thing with the weak acid and weak bases, then we can get into the salts. Yeah. Okay. Yeah. So, wait. Yeah. So you can share the. I'm not sure. You might have to have your video back on first and then share. I don't know how it works. Okay. You're pulling it up, right? You still with me? Oh. Hey, what happened? All right, we have you back. All right, welcome back. Okay, so you're sharing the thing with me before you lagged out. All right. If this is too laggy, we might switch to Skype or You can call me on FaceTime or something. Yep. Okay. Okay, so acid-base property of salt solution. So what is salt? Salt is something you create when you combine an acid and base. So the most common kind of salt, you know, is your table salt. Okay, first thing is qualitative. You need to know 4 different situations. Okay, and before I even get to that, I need to show you something first. When we have strong acids or strong bases, strong acids and strong bases, and you know what they are, right? Yeah, so you got the 7 strong acids, the strong bases. You can memorize them through and I said basically this is a single arrow to the right, so I'm just drawing an equilibrium. Just pretend it's an equilibrium, but on the right side you're gonna get a Cl minus, you're gonna get H3O plus, and check this out. The Cl minus technically is a base, right? Technically it's a base because it's a conjugate base of an acid. So if I write out that as a base, I will have Cl minus plus H2O giving me OH minus. Okay, it's not showing up right now, but is this showing up for you, the first part, the HCl plus H2O? Alright, is everything frozen right now? So we got the Cl minus, so the base version will be Cl minus plus H2O. That's gonna give me HCl plus OH minus. So you see, what I'm basically saying is this. A strong acid means it's so far, lying so far to the right side, right? It's 100% dissociation. What I'm trying to tell you is the conjugate of something that's strong is going to be very, very weak. So this, because this is strong, this is going to be very weak, such that it does not affect pH. So right now I'm going to say this. Weak conjugate. So the conjugate, doesn't matter acid or base, of a strong acid or base will be very weak. And very weak, I put that in its own category versus weak. Weak means small amount of dissociation, but very weak means virtually no dissociation. Very weak, aka no dissociation, or maybe ionization is the best word, is better word. So if I look at something like sodium chloride, and if the question asks me, hey, and this is going to be the question, first few questions is going to be giving you a bunch of salts, and you have to identify, well, is this salt going to be acidic or basic or neither? So be it. So virtually 0% ionization. So if I look at something like NaCl, this is the way you predict it. You break them apart into their ions. You go like, okay, where did the individual components come from? Na probably came from, so you got Na plus, you got Cl minus. Na plus came from NaOH. So this came from NaOH. And because NaOH is a strong acid, that means Na plus is going to be a weak, because NaOH is a strong base, Na plus is basically going to be the conjugate acid. And specifically, it's going to be a very weak conjugate acid, so it's not going to do anything. So Na plus is not going to do anything. Cl minus, where does Cl minus come from? Cl minus came from HCl, which is also a strong substance, in this case a strong acid. So Cl is going to be the conjugate base of a strong acid, so that's going to be a very weak base. So again, this is not going to do anything for me. So we got the H from HCl, so that's why they're both not going to do anything. So therefore NaOH is going to have a pH of 7 because it's going to be neutral. So let's look at another example. What happens if I have NaF? Well, NaF, let's break them down into their two components again, and we have Na plus and F minus. Na plus again came from NaOH, so if it came from a strong base, it's going to be a very, very weak acid, so it's not going to do anything. F plus though came from HF, and is HF a strong acid or a weak acid? Yeah, a weak acid means the conjugate base is also going to be weak. So this is going to be a weak base because it's a conjugate of a strong acid. It's a conjugate of a weak acid. So a weak acid pairs of weak base, strong acid, pairs of weak, very weak base. So I guess I'll write a chart here. So weak goes with weak, and strong goes with very weak, very weak. So therefore, if I were to predict NaF, what is it going to be the pH of this? This is going to be basic, because I basically combined a weak base with something that's neutral. Then I'm going to have the whole thing as a base. Does that kind of make sense? Okay. So again, what I'm basically saying here is the salt is going to dissolve in water into its components, and then you just look at the individual components and be like, hey, what is this going to do? Is this going to do anything? Na plus in this case is not going to do anything. F minus is going to do something. So therefore, this whole thing, pH is going to be greater than 7 because it's going to be a base. Situation number 3 is if you have something like, let's say, what would come from a weak acid? So maybe NH4 plus. So NH4 plus, let's do Cl. NH4 plus Cl. Let's see what pH would that be. So if you break this into its components, so if you throw this into water, it's going to break apart into NH4 plus, and you got a Cl minus. The NH4 plus came from who? So who's the conjugate of NH4 plus? So since that's an acid, basically I'm asking you, what's the conjugate base of NH4 plus? Sorry, you're slightly cutting off a bit. NH3, exactly. And is that a weak acid or weak base or strong base? Is my voice breaking up at all when I'm explaining this stuff to you? Because your voice is really laggy. I can only imagine how laggy my voice must be. Okay, let me do a few things to try to fix that up a bit.